Hi everyone. Previously, we have introduced the product set. Given a set A and a set B, the product set A cross B consists of all ordered pairs of the form xy, where x is an element from A and y is an element from B. At this moment, the choice of such ordered pairs is fairly arbitrary. Yet sometimes we might want to focus on some specific pairs in the sense that the component x is related to the component y in some specific way. For example, let A be the set of countries and B be the set of cities. Instead of taking whatever a pair consisting of a country and a city, we can impose a relation by requesting that city Y be the capital of country X. Now with this extra constraint, we see that the ordered pair France-Paris satisfies this relation, since Paris is the capital of France. On the other hand, the pair USA-New York City is no longer admissible, as New York City is not the capital of USA. Notice that this verification process of whether x and y satisfies some specific relation can be viewed from another perspective. More precisely speaking, let us consider a subset R of the product set A cross B, which consists of all ordered pairs of the form x and y, where city Y is the capital of country X. In this way, to verify whether a city Y is the capital of a country X is equivalent to verify whether the ordered pair xy belongs to this subset R. And that is precisely how we define a binary relation in general. Indeed, given a set A and a set B, a binary relation R from A to B is nothing more than a subset of the product set A cross B. If an ordered pair xy belongs to R, we say that x is R related to y, and we denote it by xRy. Clearly, this definition does not only agree with our intuition on relations in our daily life, but also provides us with a mathematical language that is flexible and rigorous enough to describe relations among objects in two sets. To start with, notice that given arbitrary sets A and B, the empty set is always a subset of their product set. That is, the empty set itself is always a binary relation from A to B. This relation is called the trivial relation. Intuitively, it means nobody in A is related to nobody in B. On the other hand, the product set A cross B is a subset of itself. Thus, it also determines a binary relation from A to B. This relation is called the universal relation, which translates into everyone in A is related to everyone in B. As you can imagine, in most cases, the binary relation that we're going to investigate is neither as trivial as the empty set, nor as arbitrary as the product set itself. For example, consider a binary relation R from the set of integers to itself, such that an integer x is R related to y if and only if 2 divides their difference, x minus y. In other words, x is R related to y if and only if x, y have the same parity. Based on this relation, we can put each integer into the set of even numbers or the set of odd numbers, and in this way we achieve a classification of integers. Also, we can consider a binary relation from the set of real numbers to itself, such that a real number x is R related to a real number y if and only if x is less than or equal to y. This relation has established an order in real numbers, based on which we can compare two real numbers and from there eventually discuss a minimum or a maximum of a given subset of real numbers. Last but not least, notice that we have already learned how to draw the function graph of the parabola y is equal to x squared. This graph is a subset of R2, and hence naturally can be considered as a binary relation from R to itself. Yet this graph completely determines the information of the function. In other words, defining a function is just a special case of defining a binary relation. Alright, now hopefully you're convinced that the binary relation is versatile in mathematics. It can help us perform classifications, establish orders, and define functions. Yet for each of these applications, our binary relation has to satisfy some specific requirements, which we will discuss in detail in the coming sections.